Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. We will be today dealing with week 9 where we will be introducing to you the next generation FET, also termed as Forksheet FETs, and subsequent to that we will be looking into complementary FETs, which is basically known as CFETs. So these two major devices, its structure, its importance and its fabrication can be shown in this week 9 lecture. So the class wise discussion, we will be first of all introducing to you the Forksheet FETs, right, and then discuss the challenges of Forksheet, how the Forksheet therefore is in a sense different from the state of the art design available to us, which means that how the current state of the art is trying to bring Forksheet in a natural fashion. We will look into complementary FET, its advancement, and in the probability of it getting industry adopted for general purpose use will be also looked into. And then the last class will actually concentrate on design challenges, and then can we optimize the CFETs for in the path towards more of semiconductor scaling. So these are the four sort of classes which we intend to take. So in the first class, lecture 1, we will be actually looking into the technology scaling challenges, which most of you must have by this time understood what are, but just to recapitulate the whole thing. Then we will look at the structural view of non-planar FETs and then the fabrication flow of Forksheet FETs. Important point, we will look also into the gate metal work function patterning, and then finally come to a Forksheet FET, and let's look at the circuit layout advantages of a Forksheet FET as compared to a standalone nanosheet FET or a bulk MOSFET. Variation analysis, which is primarily the structural or geometrical variation analysis, and then looking at the circuit level scaling, how does the scaling affect the circuit level analysis. So let me come to technology scaling challenges. Now if you look at the first part of it, what has happened is the nanosheet FETs, they are projected to perform well over 3 technology generations, from 3 nanometer in 2022 to approximately 2 nanometer in 2025, right. And if you proceed further and bring it to a very high end definition, to approximately 1.5 nanometer in 2028, according to IRDS, which is International Roadmap for Devices and Systems. Which means that if you look at nanosheet FETs, if you remember, nanosheet FETs concept was that you had the gate coming like this and the nanosheets were all attached in this manner. Remember? Let me give you a proper diagram for that, and then I will show you what do I mean by the nanosheet FET. So this is your gate, right? And then what happens is the nanosheet FETs, if it's a 3 FET device or 3 sheet device, then these 3s are the cross sectional view of the 3 nanosheets. So these are your nanosheets, 3 NS, 3 nanosheets. This is your gate, and this is NS 1, 2 and 3, and then you have at the bottom side the soy or even a silicon substrate, and on the front and back side of the screen you will have source and drain, right. And the idea of a nanosheet FET was, as you make the number of sheets larger and larger, the current disbursement sort of advantage becomes larger and larger for nanosheet FETs. So larger the number of these sheets available to you, better will be the current carrying capability of this device, and it will be the integral multiple of the number of sheets available to you. However, as you proceed for a much smaller version, the in pitch between the two sheets, that is the sheet pitch, right, the sheet pitch concept will come into picture, and this will actually go on reducing beyond a point, because you can't let the height go beyond a particular point. So if you want to introduce more and more sheets, this will be at the cost of reduced sheet pitch, right. and once you do a reduced sheet pitch, the interference between the two neighboring sheets will be relatively large, right? And therefore, what people thought that was that if you go on scaling it beyond 1.5 nanometer, this interference might come into picture, thereby destroying the very property of the FET which has been used behind it. So, by 2031, it is expected that the nanosheet FET might no longer be able to deliver the extended performance or expected performance at the cost and power budgets which have been highlighted. And that is what is shown in the red, that by 2027-28 there will be initial thrust in terms of complementary FET, and it is expected that commercially CFETs would appear around 2029. So, late 20s we will see CFETs being actually used in industry to a larger extent. Already basic idea and its structural verification and roadmap has been created. It is just that we are waiting for this to happen till 2029, and that is the reason this chapter is very, very important. Now, let me introduce to you a Forksheet. Maybe I can show you some. Let me show you a structural view of the Forksheet, and then we will come back to what I was discussing with you. Look at the figure on the left hand side. This figure is of FinFET. This is FinFET. Right, this is a planar, non-planar structure. This is a non-planar structure, and then you have nanosheet FETs, which are again non-planar in nature. Right, because the sheets are actually in third dimensions, moving up and down. And as a result, what is happening is that this is the non-planar FET, era of non-planar FET. Now, what happens in a Forksheet FET is that can we have a PMOS and an NMOS within the same substrate and separated by a dielectric wall. So, that is what is known as a Forksheet. So, you have this as your p-type semiconductor, this as N, and there is a Forksheet wall or a dielectric wall which separates between the N-type device on the left hand side and p-type device on the right hand side. Now, there will be so the drain and source are actually away from the plane of your laptop, and also the back side of the plane of your laptop, which means that what you will see here is basically there will be source and drain which will be away from the plane of the desktop, and one will be into the plane of the desktop inside. And there will be two electric lines of forces. One is the electric lines of forces which will draw the electron and holes in the opposite direction. However, there will be also an electric lines of forces which will try to basically do an interference between the two nearest neighbor sheets, either in a PFET or in a NFET. Now, there will be also a non-equilibrium level charge trapping in dielectric wall. So, this dielectric wall is basically a silicon dioxide. It cuts through the NNP layer and ends up in the metal layer. So, basically if you look very carefully, this is the Forksheet, this is the dielectric, there is an oxide layer which surrounds both these devices here, right, both these sets of devices here, correct. Because of this MOS device, they starts behaving like a ordinary MOSFET here. Only thing is that now you have stacking of these MOSFETs, right. This dielectric wall is also referred to as DW and is made up of silicon dioxide. You can also have stacked silicon dioxide plus hafnium oxide. You can also have silicon dioxide plus titanium oxide, and so on and so forth, right. What it does, it makes my EOT smaller and smaller. Now, the idea is as you change the material of the oxide layer, you do have different values of the dielectric constants coming into picture. Higher the value of the dielectric constants, better will be the coupling between the NNP layer, right, and that will be known as the coupling coefficient, which we will discuss later on. But the takeaway from this slide is that we are looking into Forksheet which was there, which is made up of two layers of nanosheet. So, if you look very carefully, this is one nanosheet, right, this is one nanosheet, and you have another nanosheet in this manner, and they are basically connected back to back with respect to each other, right. With this, we have understood the structural view of the non-planar FET, but to do that, let me introduce to you the Forksheet. If you follow IMAX scaling theory, then the gate pitch and the fin pitch, right, you will see saturation of these two quantities, while channel scaling is achieved by doing what is known as a track height reduction, also referred to as TH reduction. Now, what is the track height reduction? I will discuss that slightly in detail, but let me explain to you how do you achieve this value of track height reduction, what should be the value of the final track height. And what is a track height? Track height is basically, for example, I will give you an idea here. Let's look at the contact gate pitch, right? The contact gate pitch, if you go back to the previous slide. So, what I was showing you here is the relative scaling versus your various nodes, right? So, you had 14 node, 15, 10 node, you had 7 node, you have 5 node, 3 node and 2 node. So, as you move from a higher technology node to a lower technology node, lower and lower technology node, the relative scaling actually tends to saturate, right. So, smaller the value of the technology node, more difficult for you to scale that node, right. However, larger the value and therefore the justification, larger the value, better scaling is possible. The second aspect which you can see is that there are three important points. One is the CPP, right, and then you have the contact. So, what you have got a fin pitch, contact gate pitch, and we have the channel pitch, right. Now, this channel pitch actually tends to become much lower in case of a biased sort of device, and in case of unbiased device this becomes slightly larger in nature. You also need to look into the fact that you should have a proper fin pitch, metal pitch, and the standard cell are not violated while designing the. Now, we have already finished with the structural view of nanosheet. Let me further continue into the Forksheet FET. Now, if you look carefully on the left hand side, it is just there are two figures, right. One is basically the nanowire or a sheet nanowire FET, right, the left hand side, and the right hand side is basically a Forksheet. The difference primarily between these two is that there is a dielectric layer which separates V and N type, right, and therefore it acts as an isolation sort of region in a sense. So, there is always a P to N separation taking place in a Forksheet FET, whereas such P to N separations are not visible onto the first diagram. You can also have the dielectric wall made up of silicon nitride rather than silicon dioxide, right, and the idea is that we will have a much larger sort of epsilon, and as a result the isolation will be much proper in that case as compared to that of the current disposition. Now, silicon dioxide obviously is much better. You can handle silicon dioxide in a much better manner, easier manner as compared to silicon nitride. Now, let us look at the fabrication flow of a Forksheet FET. So, on the right hand side you see the TEM image after etching and after wire formation by silicon nitride conformal deposition and etch back, right. So, the process flow for fabrication of Forksheet FETs are that you take two stacked silicon, right, and after the silicon channel is released, HFO2 gate inner surface HFO2 gate dielectric formation start splits, a dual work function metal gate emerges, which is integrated for both N and PMOS, which is processed to an M1 BOL for electrical characterization. So, these are the metal contacts through which the fin FETs or even double gate Forksheet FETs can talk to the external world. Now, let us go by the block diagram and step by step response for the fabrication flow of Forksheet FETs. First is basically the ground plate formation, right, and this ground plate formation is relatively easy and very fast to do. Then we look into the silicon germanium oblique silicon epitaxial growth, right, and this is where you have to be very cautious in making the silicon growth proper in a proper fashion. The growth should be in a proper fashion, right, because otherwise there will be a problem of disorientation and voids being formed at various places within the crystal. Now, after the silicon channel and interfacial layer and HFO2 gate dielectric formation, dual work function of the metal gate, where integration of both N and PMOS wafers are processed up to metal 1 back end of the line for electrical characterization. So, what we do is that we pick up that metal 1 from the electrical characterization chamber and then take it forward. So, let us come to the metal gate metal work function patterning. The so the NNP scaling advantage, right, of Forksheet basically helps you to fabricate nanosheets to work at function metal patterning, right. So, there are two types of patterning, one is the non-functional and another functional. As the name suggests, the functional will give you an output in terms of some known results, while non-functional will give you not necessarily all the outputs which you desire. Now, in nanosheet, the high mask aspect ratio is challenging for patterning a well defined NP boundary, and which will result in the removal of PFETs, right. So, if you encounter PWFM, right, lateral sketch between two PMOSes, we had a discussion yesterday that the PMOS NMOSes should be kept in the middle, so that you do not have a sort of uh, problem in later on, and therefore, what we do is that we define a well defined boundary, and on the end side of the boundary we try to keep the patterning mask. Now, the p type WFM lateral etch-in between MOS and nanosheet can lead to mask undercut, and therefore PWFM removal PFET is important. The last point is that the Forksheet, the mask ratio is substantially lower because the mask edge lands on the top of the wall. So, you can see why, because the distance is so small, right. Distance is not only here, you can actually look into the distance from the point of view of, just hold on, right, from the point of view of NP boundary is substantially lower because the mask edge lands basically lands on the top of the wall, which means that if the mask edge is not away from the wall of the pan, then we are safe. If it falls on the top of your land, then we need to find out a methodology by which we can remove it. If you so basically mask undercut is a major issue which people tend to avoid while doing FinFET patterning. So, the risk of PWFM removal from PFET due to mask undercut is eliminated by physically separation of PWFM on either side of a wall. So, what you do is, rather than having a single side PWFM, we just maybe rotate it by 180-degree, so that the slight environment change is there, as well as proper inputs are there to study properly in the case. So, this is basically the metal gate functional engineering. This is to show, on the right hand side is to show to you how does a layout, or basically a device level layout, works in terms of the cross section of the device. And as you can see that somewhere around 4 into 10 to the power minus 6, this is where these values come into picture, right, come into picture. And then if you plot it here, this will come out to be 0, 0, 0, 0. And therefore, if I want to fabricate a device, then I need to ensure that it has not got the sharp p type edges, but they do have a long edge available to long end available for us. So, that is shown on the right hand side of the figure. Now, what we will be looking subsequently is that if I give you the possible layout of inverter and transmission with PFET and PFET connections. So, we can also do a device level layout. We can use an N type and P type formation in using one of the TCAT structure, and then possible layout of inverter and transmission gate with PFET and TFET is very dominant, right. And that is the major area of interest when designing the high level circuit design. Now, since some discussion on IW on the variation of your the percentage change in the on current. As you can see that if we are doing a 15 nanometer channel length, then the red colored line which has been circled, right, actually falls from approximately 15% of efficiency to approximately about 10% or 12% of efficiency. So, the smaller channel, W channel is basically the width of the channel. Smaller W channel will reduce the dimension of the device, right. Why is it so? Because when you make your FET more vulnerable to electrical coupling, you send a smaller person with a lesser vulnerability, and that will give you a result based on that. Now, the problem is that if you look at NFET of the same dimension as PFET, NFEL will lose much larger as compared to PFET, right. Then if you look at this bottom dashed line is basically referred to as yield of the student in terms of output, right. So, the output here is that it should not fall below. So, for example, I will give you an example. Say let us suppose my W channel is increasing, the width of the channel is increasing, and my the change in the on current which was very large at low values of W channel starts to fall down, right, because as your width starts to increase, though your W effective W goes on increasing, but the change in the on current actually reduces because higher width will imply a larger current, but the change will be slower and slower. What we say is, and the blue one is for the PFET. The PFETs are all blue colored graphs available to us. Now the point is, and the change in the threshold voltage is on Y2 axis. So this is your Y1 axis, this is your Y1 axis, and this is your Y2 axis. Now both the on current, change in the on current and change in the threshold voltage are changing by a large value as you move from lower WCH to a higher WCH. Look at the right hand side graph, you will see that at the width of the coupling dielectric wall goes on increasing, the current starts to fall down drastically, again the same result, that the threshold voltage change is also very large in this case, and this is basically for both NFET and PFET into consideration. And in the first case, the width of the wall has been kept to approximately 14 nanometer silicon nitride, and in the second case the width of the channel is kept at 15 nanometer silicon nitride. So, we define yield criteria as in the second graph, when you delta I on is approximately 20% sort of a benchmark. Anything greater than that will give you a much larger value of ion. Now, let us come to a power performance area advantage for Forksheet and nanosheet, right. So, basically PPA, which we refer to as a power performance and area, is basically the governing factor for the determining the utility of nanosheet FET. So, if you look at the left hand side, we see a 42 nanometer CPP sheet layer with 18 nanometer MX pitch. The pitch between two master layer is 18 nanometer, and then you have this nanosheet width versus 5T cell as your MX for a buried power rail which is given to us. And the first one is basically nanosheet FET with 21 nanometer as the width, and the second one is Forksheet FET with effective width of 21 nanometer, right. What we see is that if you plot on, if you look at this graph on the below, then this is the active power versus the channel length, and as you can see, the channel length increases, the active power increases irrespective of the fact that whether you used nanosheet, 4-sheet nanosheet or a 3-sheet nanosheet, right. It is always increasing in almost a non-linear fashion, but it is increasing nonetheless at very high values of T. Now, let us come to the scaling of devices at circuit level, right. Now, this is basically a data from the VLSI Technology Symposium, where the first times IMEC Forksheet was shown to the public. Now, this is the place where you will see that even if you look at the power versus frequency, as the value of your frequency goes higher and higher, the effective power actually increases, because it is almost like a parabolic increase in the power dissipation of individual devices. If you look at the right hand side figure, This shows you again the relative scaling from 14 node to 2 node. And as you can see, when your node voltages are much higher, or your node structures are much higher, it is difficult. So the variation is almost negligible if you change your node from 10 to 14 to 10. But even between 10 to 7 is acceptable, but anything beyond 10 is not a good idea, right? And that's the reason you see, as you move forward, the green colored and the fin pitch and the CPP pitch tends to saturate, whereas C channel tends to go down, right? And this is a good idea from the point of view of FP and CPP. Then people went for a ring oscillator. So this is basically the design of 15 stage using ring oscillator, and we saw that as the power goes on reducing, the width of the ring oscillator design goes on increasing, right? And that's the major advantage which you get from a FinFET, that it's not always a win-win situation. For example, in ring oscillator, you might achieve a loss also depending upon the power utility of the design which you are using. Now, so that's what we have recapitulated as far as what we have learned is two things. We have learned, first of all, basic idea about Forksheets, and then we looked into design and development of Forksheet FETs. Third thing is, we require to have a thorough understanding of the Forksheet FET in order to appreciate its working principle, and we can also design through Verilog a simple ring oscillator in order to achieve the values of the output. So I can do a sort of a device, sort of a circuit co-design, right? This is device circuit co-design, right? And why I'm saying co-design, because many a time iteratively you have to come back to the original design to make changes for the upcoming design. So this is what we have learned in this small duration of half an hour, and now we will go for the next stage later on. Thank you very much.